Hi, hello and welcome to DV Club today. This is a special session where we're just going to be covering embedded UVM. Again, thank you to our sponsors, Agnesis, Cadence, Synopsys, Bereka, Imperas, ARM and ST, and to TestSolve who host the events. As I said, we've got one speaker today, Puneet Goel, who works for Coverify Systems Technology based in India, and he'll be speaking for an hour, and then we will close the event after 1 hour. So these are UK times, and we'll be closing at 1 o'clock UK time. Okay. So we will ask Puneet to share his screen, and once he's done that, then we'll start. Puneet, can you share your screen, please? And I'll make an introduction before you start.
Give me a second. I need to share my screen. Just a minute.
Yeah, if you go full screen mode, please.
Okay.
Can you go full screen? You can't see everything.
Can you see my screen?
Yes, yes, we can. Okay, so yeah, welcome to DV Club. As I mentioned, Puneet Goel is from Coverify Systems Technology LLP. He's the CTO based in India. He is an open source hardware verification enthusiast. He's the lead developer of eUVM, an open source multi-core-enabled implementation of the UVM library in the D programming language. And the title of his talk is HPC-Powered UVM Testbenching and crafting high-performance multi-core verification IPs using UVM. Okay. So over to you, Puneet, please.
Thank you. So HPC, as you all understand, it stands for high performance computing, which includes multi-core computing as well as other methodology, basically other techniques to make high performance computation. The curious case of RISC-V verification. So this is kind of the motivation for our work, one of the motivations. When you verify a high-performance, high-end RISC-V core, it may take as many as 10^15 randomized instructions. So the same would be true for ARM processors as well as for any other processor. Actually, this number basically is coming from a paper, which was a white paper, which is written by ARM. And so now the point is, how do you generate so many randomized instructions? RISC-V-DV, which is a popular open source RISC-V random instruction generator written in system Verilog. Basically, our team at Google anchored this project. So it is able to generate 10,000 instructions per second. But if you map the large number 10^15 to this performance of 10,000 per second, it will take 3,000 machine years to generate these many instructions. Okay, so this is the motivation, and also that verification as chips become more complex. So verification is becoming more and more compute intensive job. So any team any verification team would have hundreds, if not thousands, of simulation servers. And this is going to increase with open source hardware because you'll need continuous integration kind of stuff. So this is the agenda of the talk. We'll see why contemporary verification tools are slow. We'll look at how to make verification fast, and then we will have an introduction to embedded UVM. And then we'll have some code walkthroughs. First walkthrough is going to be very later powered register verification. And second walkthrough is going to be SoC FPGA co-emulation. We'll put the design on the FPGA and we'll run the test bench on the on the programmable, on the HPC part of the SoC FPGA. And then we'll look at multi-core UVM constructs. And finally, there will be a code walkthrough where we'll look at RISC-V-DV implementation, which is multi-core enabled. So to start with, why test benches are slow. As chips become more complex, as processors become bigger and chips become more complex, we have reached a point where the clock frequency has stopped scaling, and as a result, till 2005 or 2004, 2005, that kind of time period, as the chip complexity grew, the processor frequency also grew. So meaning that by you are verifying bigger chips, but you also have a machine which is capable of running faster. Okay, but since 2005, the performance of the so this is all logarithmic graphs. So the performance is not increasing at that scale, and therefore you are verifying larger chips, but you don't have machines which can perform that much faster. Okay, so since 2005 till 2005, it was an era of free lunch, meaning that you don't have to do anything. You just wait for when you move to the to a new project, you have better machines to verify. So the new project is bigger, but the machines are faster, which run the simulation are faster. But starting 2005 is the era of high performance computing. So you have to work hard to make applications which can run faster. So this is what we are going to look at. There is also a memory wall wherein the DRAM performance hasn't been growing at the same rate. Like DRAMs are becoming faster. DRAMs are becoming faster at something like only 7% per year, but they are becoming bigger. Okay, so memory wall basically says that if you want to make high performance applications, your memory footprint remains. You want to make it low memory footprint because there will be a cache limitation. The cache will be smaller. So what makes contemporary verification tools slow? One is lack of HVL. So now this HVL is important. When you talk about multi-core simulators today, only the RTL part of the simulator is multi-core. The hardware verification language part is not multi-core. Scheduler semantics of system Verilog is done in such a way that testbench parallelism is not enabled. We'll talk about it later. Then poor native language performance. We are also going to elaborate on this. DPI bottleneck, and finally lack of generic programming, as well as opaque data containers and algorithms. When you are using system Verilog queue, for example, you don't know what kind of overhead, if you are inserting inside the queue, or if you are growing the queue on either side, what kind of overhead it is going to have, because the data structures are opaque. And then there is no generic library like algorithmic library, etc. So when we talk about multi-core simulators today, only the RTL part is multi-core enabled. Testbench, which is behavioral, is not multi-core enabled. A typical scheduler for system Verilog, you have RTL simulation, so RTL events in separate phases, and testbench events are in they'll be sequential. So you'll have RTL events, and then later on you will have testbench events. Okay, so if you make RTL simulation multi-core enabled, so even if you are running say 32 parallel threads, this testbench is going to be a bottleneck because testbench is not multi-core enabled. So if your original testbench was taking 20% of your simulation time, I mean, in case where your RTL simulation was also not multi-core. So if testbench is taking 20% of time. Even if you make your RTL multicore, you can't perform, you can't have efficiency better than 5x because testbench will remain sequential. So there is a slight issue with the way system Verilog simulator is. So testbench will be simulating after RTL events are done. Okay, so it's kind of that way. Like when testbench is simulating, nothing will be happening on the RTL. So RTL simulation will be static, and after that, the testbench tasks will take over. And once the testbench tasks are done, then it will go back to RTL simulation. So very small periods of time, you will be interlacing RTL simulation with testbench simulation. As a result, even if you create constructs in system Verilog for parallelization of testbench, what's going to happen is the threads which are doing RTL simulation, they are going to stop, and then the context switchover will be there. So they'll load testbench specific memory, and then they will follow it up with testbench task execution. And finally, when the testbench tasks are over, then again the RTL simulation has to start again. So the context switching is going to be an issue in case you are trying to make test benches multi-core in system Verilog. By the way, I mean, system Verilog doesn't have those constructs that you can make test bench part of the simulation multi-core. But even if you want to do that, that will have some issues due to the scheduler semantics. The next consideration is TLM. TLM is basically requires isolation of data from time. In system Verilog, it's not done. So whenever you are talking about byte, integer, or any other integral type or bit vector types in system Verilog, there are associated events. So there are change events whenever some data is changing. So a change event will be triggered, whether or not you are going to listen to that. You are waiting for that, but there are associated events. So it's as if in system C, if you are using SC signal, okay, so that's more equivalent to what system Verilog data types are. Okay, so imagine system C, which doesn't have integer or which doesn't have bit vector data types, but only SC signals. So your simulation is going to be slow, right? Because you'll not be able to implement TLM kind of methodology. So algorithms coded in C++ run an order of magnitude faster than system Verilog, though there are no benchmarks. But if we take a small algorithm which calculates Fibonacci series, now I take Fibonacci series because this is tree recursion and it's going to take time. So if you run these two on any system Verilog simulator and C++ compiler, you're going to see an order of magnitude more than that. So that kind of difference in speed. The third consideration. So we talked about multi-core, we talked about native data types, absence of native data types in system Verilog. Third is also related to absence of native data types. So system Verilog integrates very well with Verilog, but it doesn't integrate so well with emulation systems because of the DPI layer. So the DPI layer is going to have an overhead, primarily because it doesn't have native data types. So integer in system Verilog is going to have a different memory footprint compared to integer in C or C++. Now we look at what are the considerations if we want to make a fast HVL, then basically negation of all these points that we discussed here. So if we want to make a fast HVL, we need ABI compatibility with C, C++, also because in the coming era, you will have hybrid processors, and hybrid processors are going to have large FPGAs available wherein you can map your design and just run the test bench along with that. So every server processor, if it has FPGA cores available, and that's going to happen because AMD bought Xilinx and Intel bought Altera. So that's the primary motivation. So with hybrid processors, almost every server and machine is going to have processor plus FPGA. So you'll be able to map your design on the FPGA and run the test bench on the processor. So, but for that, it's very important to have ABI compatibility with C and C++, native data types, parallel programming constructs. And then for implementing universal verification methodology, you need object-oriented paradigm, just like system Verilog. So all these, if you figure, then universal verification methodology needs whatever is provided by system Verilog. Then you need domain-specific language support. Okay, because verification is a domain, and we need that kind of support that we are able to build the verification features on top of a language. So we need user-defined attributes. We're going to take a look what these are. We need compile time code introspection, which is very useful for making a very fast, efficient constraint solver. We need compile time function evaluation and generative programming, which is different from preprocessor macro expansion. So basically, you are able to introspect your code, which is maybe written at the end by the person making the verification IP, but the library is able to introspect what are the components inside it, and it's able to generate constraints based on the constraint specification given in the user code. And finally, it needs to be open source, because with the open source hardware, there'll be a lot of cloud deployment of verification systems. Okay, so for example, when we tag an integral variable as random, okay, so user-defined attributes come handy. If they're not there, then for example, the Crave library uses templatized wrappers over integral types, which end up making the integral types pretty having much bigger footprint, and then that kind of wrapper types will make the code slow. Okay, so similarly, for introspection, I already talked about how it makes it possible to recognize random variables. So CTFE or compile time function evaluation is going to make it easy to parse constraints, and generative programming is going to write the final code for generation of constraint solving. ABI compatibility with C, C++. So what we did was we took object-oriented languages. Some of these are partially object-oriented, and we took the mainstream ones. They also need to be systems programming languages, because we need we need ABI compatibility with C, C++, and we need interaction with the kernel when we are, for example, trying to interface with FPGAs. So we took the mainstream ones, and we find out which ones are suitable for the verification need. So C++ does a lot of things, but it's not efficient for constraint solving. Like if you solve the same constraints in embedded UVM, you try solving them on a C++ based constraint solver like Crave, you are going to have a magnitude of an order of magnitude performance difference. Like it's going to be 20 or more times slower, even if you don't have, like, even if you are not using multi-core in either of them. So just with single core C++ and single core DLang, C++ constraint solvers that exist today are 20 times slower. Go and Rust, they are not typically object-oriented. So those features are missing. Like Go is, you can say it is object-based, but not object-oriented. Rust has a very different, you can say, object model. So it has object ownership kind of concepts, which make it very difficult to plan a UVM kind of library. Okay, so finally we come to DLang, or the deprogramming language. And we find it has garbage collector, it has first class multidimensional and associative arrays, and very, very developed metaprogramming semantic, which make it possible to write a very efficient constraint solver as well as functional coverage constructs. So constraint solvers, you have system Verilog, you have system C verification library, Crave, and you have Python VSC. So there is a comparison, and DLang, the constraint solver we developed in DLang, it can solve any constraint that can be solvable in system Verilog. We took RISC-V-DV as a reference project because it has very complex constraints, and we were able to solve all those constraints in embedded UVM. And compared to that, in Python, we were able to solve some constraints, but not all of them. And Python constraint solver is way, way, way too slow. DLang constraint solver is much faster even compared to system Verilog. We are going to see some examples later. So a note on Python performance. I'm specifically mentioning Python because there is a lot of movement towards Python when we talk about verification. So Python has been benchmarked against C++, and the benchmark says it's 57x slower. So you can take this small program to generate prime numbers, which are less than a million, 10 million actually, and you'll find the Python version is going to run 50 times or more slower. Okay. Besides that, as the data structure sizes grow, Python data structures don't perform very well. So these are the considerations. So you don't want to move in the future without knowing the performance aspects of your test bench. The first code walkthrough, very later powered register verification. So let me. Okay, so I'll make the font size a little bigger. Okay, and this too needs to grow. Okay, so we have a patched version of Verilator, and that patched version is able to create wrappers over the C++ models automatically. So let me say make clean and then say make. Okay, sorry. This is make clean. So there is some small issue with the make file, it seems. Okay, this is an issue with the path setting. Just give me a second, I'll fix it. Shop tools, embedded UVM. Make clean. Okay, so just a minute. Probably a very later related issue. So let me explain the code first, then I'll set it right. Okay, so what we are doing is, in the RTL, we have a register map, okay? And this is the register decode logic, a typical register logic that you may have in any SOC. And in the test bench, we have, this is the whole AXI test bench, and including the Reg package. So as you can see in the test, we are doing reads and writes on the registers, and kind of elaboration phase just on that. So this is the test. It's a directed test. We are reading and writing into certain registers. Okay, and then path equal to /user local bin. I need the right path to very later. Probably I'll get it by loading the module. Very later. Okay, so sorry, I'll take this example in the end if I get time, but let's progress with the other examples first, because I'm not able to find the right version of very later. Somehow I messed it up. Okay, so overall, embedded UVM is built on top of D language. We get certain features because we built it on top of D language. So these features are implicitly there in D language. Then we built a discrete event simulator on top of that. And we built queues and bit vectors, constraint solvers, functional coverage. We have the complete implementation of IEEE 1800.2 standard. And for integrating with or interfacing with a Verilog or VHDL, we have VPI or VHPI based interface. It's a pretty complex implementation running into hundreds and thousands or hundreds of thousands of code lines. If you compare efficiency of D compared with C++, then the same example that you do in C++, wherein you are calculating primes less than 10 million, you do it in the equivalent code in D. So you'll find efficiency of D on par with C++. It's high performance. We have multi-core test benches because we have multi-core enabled VDD solvers. We are using Z3 for more complex constraints. So there is a SAT solver there, and that too is multi-core enabled. So it's the world's only multi-core enabled UVM implementation. Then on top of performance, we also have productivity features. So you don't have to use pointers, though pointers are there. So all the efficiency stuff is in the library, but the end user doesn't have to use pointers because you have first class arrays, associative arrays, and just like system Verilog, class objects are handles rather than pointers. Okay, and there is automatic garbage collection. So the end user doesn't have to worry about memory management. So it's kind of best of both the worlds. You have systems programming language with automatic garbage collector. So you have very high productivity because of the language capabilities as well as very high performance. And then the constraints that we implemented, the syntax is very much like system Verilog. Okay, so this particular thing I'll be running in the end. I just need to pick the right very later version. So I'll do it in the end. Then the next code walkthrough is where we map a design to SoC FPGA, and on the same SoC FPGA, on the ARM processor, we run embedded UVM testbench. Okay, so this becomes very lucrative because SoC FPGAs come with standard, like the boards come with standard. The boards come with standard Linux or Android images, so there is not like if you go for emulation platforms and you want to run Linux on an emulation platform, the system bring up itself is going to take a lot of time. With SoC FPGAs, you get standard Linux, and you are able to load it on the board and just have the peripheral or whatever subsystem you want to verify, you put it on the FPGA. So we take an example, we put SHA-3 RTL on the FPGA, on the programmable logic. So we have a system Verilog simulation where this gets simulated, and an embedded UVM test bench is able to verify it. We also have the same example done in SoC FPGA where the design gets mapped to the FPGA, and with some changes to the test bench, because now instead of interfacing with RTL, we are interfacing with FPGA. So using Linux drivers, etc. So we are able to verify design which is mapped onto the FPGA. So typically, all the interfaces in this example will be handled by volatile reads and writes into the peripheral registers. Okay. Now this example we are going to run on Linux, but we are able to cross-compile for Android as well as iOS and Windows platform as well. So your embedded system in this case is running Linux. So we have an ultra-scale Zinc board, and we will be running the test bench on the processor, and the design will be loaded on the FPGA of the same processor. So in this one, okay, yeah. So this particular FPGA, I can say LS CPU with more. So we are having some Cortex A53. It's ARC64 architecture, and this is a ultra-scale Zinc machine. And we have cross-compiled the test bench, and the test bench is named, the executable is named SHA-3. So just like system Verilog, we pass the name of the test. The test lies in a module called AXI for SHA-3. The name of the test is random test. So we run it, and it's running right now. It takes about 10 seconds to do, I think, 1,000 sequences. Okay. We can also use, for example, the same stuff like you have in system Verilog, verbosity equal to, say, debug. There is a spelling mistake. I need to make it verbosity equal to debug. Okay, so the same way that you do it in a simulated test bench, the same way you are able to do, you have everything, like we have the complete implementation of IEEE UVM standard. So you can do type overrides, factory overrides, all that stuff is there. Okay, so how does the test bench look like? Okay, let me just cover this part, otherwise I'll run out of time. So the test bench, in addition to the phases, the test bench can also, like in this connect phase, for example, I'm connecting to the FPGA. So I'm mapping the FPGA memory as virtual memory. And then in the sequence, etc., instead of the driver, sequence will remain same. In the driver, I will be reading and writing into memories using software instructions rather than a hardware BFM. So the hardware BFM, just like any emulation system, it is actually synthesized and part of the FPGA. And we are reading and writing on that. So a very basic primer to how multicore is done in embedded UVM. Like any multicore system, when you architect a multicore system, it's all about shared variables. So like in system Verilog, when you are having multiple verification IPs, there's not much sharing between the IPs, but the UVM library would have shared variables. So for example, the printer is shared. Okay. So wherever there are shared variables, we need to protect them. We need to synchronize them. So this is actually a verbatim code from UVM printer module inside the UVM library implemented in D. So when there is a shared printer, we need to synchronize over that. So this is what I mean when I say system Verilog doesn't have multi-core constructs for a multi-core HVL. If you want to make a multi-core HVL, all the shared variables need to be synchronized, and that synchronization semantics need to be supported by the language. Now there are multi-core, we implement a multi-core simulator first. So there are basically two parts of a simulator, of a discrete event simulator. One part is where the events and the tasks are kind of, there is some amount of scheduling or bookkeeping. So the scheduler does all that work where it creates lists of immediate tasks, immediate events, and timed events, as well as the tasks associated with these events. And as these events get triggered, the tasks need to run on the simulator. So primarily, the major opportunity in a multi-core simulator is to make the executor, or when the tasks are getting executed, you can run them on multiple threads. Okay, so this is what embedded UVM does. It runs the tasks on multiple threads. Whenever you are running tasks, whether it's multi-core or single core, every task, I'm talking about something similar to system Verilog tasks. So every task, it will load. So so for example, in the beginning, the task is waiting for an event. So when that event occurs, it will load the context, meaning thereby the task needs to start running, and therefore all the variable values of that task need to be loaded in memory. Okay, so that kind of context switch needs to be there, the program counter, etc. Everything needs to be switched, and then the task will execute. And finally, when there is a blocking statement, when it starts again, it waits on an event, so it needs to give away to other tasks which need to run. So it needs to store all the variables, the whole context, okay, all the stack variables as well as whatever the local variables are. So all those need to be stored in the memory, and then the next task takes over. So as you can see, with every task, there's going to be a bit of overhead. So to make multi-core or any efficient simulation, you need to make sure that the tasks are taking a lot of time, so that the tasks are doing sufficient amount of work, and so that the overhead is minimized. Okay, so we are going to see what are the ways of doing that. So in embedded UVM, we implement a special kind of tasks. So these are worker tasks. Okay, so these are part of the simulation in as much as they can share memory with the simulation, but then these tasks will not have a time context, so they won't wait, they'll keep working. Okay, so meaning thereby, like for verification, for example, my sequencer will need sequences. Now there is nothing with respect to time that I need to do in a sequence. I just need to randomize it. So I'll have a worker thread for that. The worker thread will keep on randomizing sequences and making them available to the sequencer. Okay, and the sequencer takes them and moves on. So there needs to be some communication constructs for that, like how the sequencer catches a sequence from an independent asynchronous thread. So we'll talk about it in the next slide. So this way, we can have virtual sequences which are fed by one or more threads. And all those threads could be running in parallel. So they continuously generate sequences. And the virtual sequence, which is part of the simulator, which actually has blocking and non-blocking kind of stuff. Like it has events. The streams which are generating sequences don't have events. They don't have any context related to time, but the virtual sequence has. The virtual sequence can keep catching randomized data from the streams and keep moving on. So this avoids all the overhead that will be there because of the scheduler part of the simulator, as well as because of the context switching. So all the heavy lifting part, like mostly it is related to sequence generation, randomization, as well as the reference model sometimes. All that can be handled by worker threads. So for communicating between normal tasks which have related events and the asynchronous threads. So in case of system Verilog, for example, when we talk about TLM FIFO, on both the ends, it is controlled by timed events. In case of asynchronous FIFOs that we implement in embedded UVM, so for example, if we are writing a sequence from a task or from an asynchronous worker thread, so it will be controlled on that end by a semaphore instead of by a simulator event. But the guy who is reading it, that part is controlled by a simulator event, and vice versa. If we want to write from, if we are passing data from the simulator to an asynchronous thread, so that will happen by having event controlled gating, so to say, on this end, and on the read end, you have a semaphore controlled gating. Okay, and then asynchronous to asynchronous is always semaphore based. So finally, we also have, like in system Verilog, you have a fork, and fork will generate multiple threads, right? Multiple tasks. And all those tasks will then be run sequentially. In embedded UVM, you can set the thread affinity of a fork. So if you look at the code out here, then we are forking out multiple tasks. But then so this is only creating them. The tasks will not start running unless we join them. Okay, so we created them, then we set the thread affinity so that they run on multiple cores. We set the thread affinity, and then finally we join them. Once we join them, they start running on multiple threads. Okay, now coming to processor verification, primarily over here, I'm putting why processor verification is tough, especially for high-end processors. There are so many permutations and combinations in which instructions can execute. And if you include out-of-order instructions and complex instruction pipelines, then literally they are like, that's why we say like it needs about 10 to the 15 instructions randomized instructions, that kind of scale needs to be there in verification. Typically, we are going to look at RISC-V-DV generator. We have an embedded UVM port of it. So it will generate assembly instructions in a file which need to be compiled and linked, and then the binary will get loaded into the test bench. And we are not going to take a look at the rest of the stuff. So this is just to give the context how RISC-V-DV generator generates stimulus for processor verification. Okay, now there is an alternate way of doing it. So instead of linking it using a linker, the RISC-V-DV generator can directly generate the binary file as well. Okay, so but that's not something we'll explore. We'll just explore how it generates the assembly language file. How the generator itself works, like if you tell it to generate, say, 1 million instructions, then you also need to tell it how many functions need to be there, which basically embody those 1 million instructions. So say I'm saying there are going to be 50 functions, then it will create 50 functions of randomized sizes. And then in the body of those functions, it's going to fill 1 million divided by 50. I mean, on average, that many, though the size of the functions will be different. So on average, it's going to insert that many instructions per function. Okay, now the body of the function is also going to be like, first it creates a big random dump. So like whatever you see in blue over here, these are just a random dump of instructions. Okay, so these are, so to say, standalone instructions which are not part of any sequence. So it generates a big random dump, and then it generates a sequence of directed streams. These are not like, these are again randomized, but the functionality of these streams is modeling different hazard conditions, right? For processor, like you have in a processor architecture various possibilities of hazards. So all those hazards, etc., are modeled in the directed streams, and those will be inserted inside the function body that way. So typically, a sequence so when you are inserting the second sequence, it cannot be inserted in middle of the first sequence, but it can be inserted anywhere else. And finally, when the functions are created, so you need a way to kind of link all the, like one function calls the other functions and returns that kind of jump instructions need to be inserted. So this is a standard code. This is a community-driven project, part of CHIPS Alliance, and we have a RISC-V port. We have an embedded UVM port, which is also we have donated to CHIPS Alliance. But the latest version of the embedded UVM code is in the GitHub repository for Coverify. So very quickly, I'm going to run this. So this is a machine. I've taken it on the cloud. So if I say ls CPU, this is AMD processor, and this is 48 physical and 48 virtual. So basically, this is the address sizes, but there are 48 processors. Okay, and this is a VPS, actually, virtual private server. So actually, the machine is having 64 cores, but I have rented out 48 out of them. Okay, so as you can see, there is cache, and this cache is important because you can see this is about 1 gigabit of cache. So the point is, if you run multiple simulations on this server, then that cache will be shared between the simulations, and all the simulations are going to become slow. Okay, but in case you are running one single simulation, which is multi-core, then since it's only one simulation, the memory is shared, and therefore cache is shared in a better way. So what we are going to do is we are going to run some, we are going to generate some tests here. So right over here, I need to go to dev eUVM, no, not in eUVM, RISCV-DV. And then there is the eUVM code, and we have a build directory. And I'll just say make run. Okay. So now this is generating 100,000 lines of count of instructions, okay, in 6 seconds. So this is not multi-core. This is on a single core, and it's generating 100,000 in 6 seconds. If you do that on any system Verilog simulator, it may take about 5 times this much time. Okay. Now what I'm going to do is I'm going to generate more. So I'm going to run another test, which is slightly simpler test, and I'm going to generate 1 million instructions. So actually, I'll make it 10 million instructions, and I'm going to do it on a, say, 10 million instructions on threads equal to 16. So it's going to use 16 threads. Okay, so this is going to take the instruction generation part. That's the part we have made parallel. The other parts where it's revisiting the instructions, and it's it's kind of doing a linker's job where it's linking all the functions together. That part we haven't done in a multi-core way yet. So you can see it took 20 seconds to generate 10 million instructions. That would be about 500,000 in a second. Okay. So after that, this much time was taken to write out the file and to do, so the writing out of the file is taking 17 seconds. So you can see randomization is happening almost at the same rate, where the string formation of that instruction, which needs to be written into the file, so that part and randomization is taking almost the same time, because randomization is done in a parallel way. So overall, using 16 threads, the randomization part we are able to optimize. So if we don't do 16 threads, if we do say 1 thread only, and we do 1 million instead of 10 million. So instead of 10 million, 1 million is also going to take about 20 seconds, because we are using a single thread. Okay, so I don't have much time to go through the code, but if there are any questions, so you can see it took 18 seconds to randomize, and then it took less time to generate the strings being written into the file, because you only have 1 million instructions. By the way, the generated code gets written here, and it's this kind of code which gets written. So the instructions are completely randomized. Okay, so if there are any questions, we can take those, because there are only 5 minutes left.
Hi, Puneet, can you hear me okay? Mike here.
Yeah, hi, Mike.
The first question was on slide 8, please. Is there any way to minimize the switching time in slide 8?
Slide 8. See, this is what memory walls are typically about. Like, basically, the caches are going to be repaged. There's going to be some paging on the caches, and that's why the time is going to be. It's basically related to the memory wall over here. If L1, if it's an L1 access, it's much faster. But if things have to be taken from the DRAM, it's going to take 50 times more time. So whenever there is context switching, all the caches will get refreshed. And it's in case it's a big simulation with huge memory footprint, so all that memory will, all that time will be extra.
Okay,
so
thank you.
What we are doing typically is we are running the test bench parallel to the simulation. So there are different threads which run the simulation, and the test bench runs on separate threads.
Okay, and they have their own cache. Do those threads have separate cache?
Yeah, but caches are on chip, and the largest cache you can have these days is 1.5 gigabyte.
Okay.
That's all. Like that's the L3 cache, by the way. The L1 and L2 caches are going to be smaller.
Yes. Okay.
Typically, like when I'm running this simulation, the memory footprint for writing out 10 million instructions is 14 gigabyte. It's going to be similar in system Verilog.
Okay. Okay. Thank you.
If you
Second
instead
question.
of running one simulation in system Verilog, if you try running 10 simulations, then it's going to take 140 gigabyte, and that's why the caches will be all congested.
Question 2 is, can you give an example of the constraint not solvable in other languages which were solvable in DLAM?
Yeah, so let me, this is a remote machine. I'll open RISC-V-DV. Oh, sorry, I need to be in work and then put code and then RISC-V-DV. So if you take a look at embedded UVM, then all the constraints, for example, if you look at the instruction gen config, so you find some constraints over here. So if you look at the constraints, they are very similar to how you will code them in system Verilog. So there is some boilerplate code, like instead of just putting constraint, I have to put constraint bank queue. But in addition to that, the constraint syntax will be very similar. So we have every kind of constraint. We have constraint.
The question was,
constraint
an
mode,
example
etc. Everything
that you can solve here that you can't say solve in system Verilog, for example.
Yeah, so we have soft constraints, and so there are 4 constraint solvers in there. One is for single variables, like if you are just saying a equal to 32 or whatever. Then there is a solver, BDD solver is there, stat solver is there, and then finally there is a solver for weighted constraints.
Okay, so you're saying that you have more powerful SAT solvers here.
See, all this ability to do things faster than system Verilog comes from the fact that my variables are integers. So they really have a small footprint. In system Verilog, you will be interfacing. So all the solvers will still be in C, C++. So you will be reading and writing into variables which are not native.
Okay. Okay. I think we've run out of time, so I'll just switch back to my screen. I must say, first of all, thank you very much, Puneet, for the presentation. I will share my screen now.
Mike, I have made you the presenter.
Yeah, thank you.
Mike, the screen is blank.
It shouldn't be.
Yes, now I can see.
Okay, so thank you for participating today, and a special thank you to Puneet. We will share the recording of the presentation and the PDF. That will go onto the website. You can see there the TestHub website. You can access that. You should be able to see the PDF later today and the recordings shortly. If you've got any ideas, just email me, mike.bartley@testsolve.com. Hopefully easy to remember, mike.bartley@testsolve.com. We had a lot of ideas and presentations following the verification futures, and we're going through those, but we're always open to suggestions to get more ideas and more presentations. Here's our provisional program for DV Club on the 5th of September. We have cache coherency automated verification. 28th of November, we have auto generation of verification infrastructure for IP to SOC level. We have our verification futures. The University of Reading has passed, and all of those are now available on the website. Our next big one is 14th of September, which is in Austin in the US. And you can reserve your place for that now. You go to the TestSolve Verification Futures website, and we have our first test club on the latest silicon test strategies and techniques, and that is next week on the 18th of July. Okay, thank you again to our sponsors, Agnesis, Cadence, Synopsys, Brecker, Impress, ARM, and ST, and thank you for TestSolve for hosting. Thank you very much, and you'll receive an email regarding the PDF and the recordings. Thank you. Thanks, Puneet, as well. Thanks again, Puneet.
Thank you. Bye.
Thank you. Thank you.
Thank you, everyone.